What if I told you the world's smartest AI researchers might actually have no idea what AGI really is? Some call it humanity's greatest invention. Others think it's just Silicon Valley's favorite marketing scam. And right now, AGI has become a giant broadcast test for the tech industry. Everyone sees what they want to see. For years, the AI industry has been obsessed with one idea: just make the models bigger. More GPUs, more parameters, more data, more scale. Researchers even gave this era a name, the Embiggening. And to be fair, it worked. AI went from autocomplete to writing code, generating videos, and sounding terrifyingly human. But beneath all the hype, there's a growing problem nobody wants to talk about. What if scaling alone is not enough? Right now, the AGI conversation is flooded with extremes. One side thinks AGI will become a digital god that solves every human problem. The other side thinks it's just a buzzword designed to boost company valuation and farm engagement online. And honestly, both sides may be missing the point. Researchers like Melania Mitchell argued that AGI won't be achieved through flashy demos, viral tweets, or doom posting about AI taking over humanity. It will require something much slower and much harder: actual scientific breakthroughs. Because today's AI systems actually have massive weakness hiding underneath their impressive outputs. They can mimic intelligence, but do they truly understand? That's a completely different question. Here's the uncomfortable reality: the just scale it bigger strategy is starting to hit limits. Training modern AI models already consumes absurd amounts of electricity, and high quality internet data, we are running out of it faster than people realize. Think about it. The internet only contains a finite amount of human created knowledge. Once AI companies consume most of it, what happens next? At some point, brute force stops being a superpower and starts becoming a bottleneck. The scary part: the entire industry may have mistaken a temporary shortcut for a universal law of intelligence. Another major problem is that we have become obsessed with AI behave like humans. But intelligence does not need to look human to be powerful. Airplanes don't flap their wings like birds. Submarines don't swim like fish. And future AI may not think like humans either. Maybe true intelligence is not about perfectly copying human behavior. Maybe it's about adaptability, efficiency, reasoning, learning in completely new environments. The future of AI might belong to systems that are fundamentally alien in how they think. And that idea terrifies people because it forces us to abandon the fantasy that AGI will simply become a digital versions of ourselves. Most people define AGI using human level intelligence. Can it pass the bar exam? Can it write poetry? Can it beat humans in specific tasks? But honestly, these are pretty weak definitions. They measure imitation, not intelligence. And according to researchers like Pei Wang, we have been looking at AGI the wrong way this entire time. Because intelligent is not about sounding human, it's about adaptation under limited resources. Under this framework, AGI is not a super chatbot. It's something far more powerful: an artificial scientist. Think about what scientists actually do. They don't just repeat information, they form hypotheses, run experiments, adapt to uncertainty, discover entirely new knowledge. That's real intelligence. An artificial scientist would be able to prioritize goals, plan experiments autonomously, learn cause and effect, and decide when to explore new ideas versus using existing knowledge. In other words, it would not just answer questions, it would actively investigate reality. This is a complete different level of capability. Today's AI models are incredibly impressive, but most of them are still giant prediction machines. They remix patterns from massive datasets. They don't truly understand the world the way a scientist does. And here's the bigger issue: modern AI requires insane amounts of compute and energy. Entire data centers, massive GPU cluster, electricity consumption comparable to small countries. But if intelligence requires infinite resources, is it really intelligence or just brute force? Because a truly intelligent system should adapt efficiently, not consume unlimited power every time it learns something new. This changes the entire AGI conversation. The goal should not be building an AI that perfectly imitates human conversation. The goal should be building a system that can learn efficiently, adapt independently, operate under certainty, and interact with objective reality. That's why the idea of artificial scientists matters so much. It shifts the focus away from flashy demos and human-like chatter and towards something deeper: real understanding. We are currently living through what researchers call the Embiggening, the era where AI companies threw absurd amounts of data, compute, and GPUs at gigantic models. Models like GPT-4 became the peak of this philosophy. train on nearly the entire internet, scales to insane parameter counts, and suddenly AI can write essays, code application, and pass professional exam. It felt like magic, but underneath the hype, cracks are starting to appear. The first problem is simple. Scaling is becoming ridiculously expensive. Modern AI training consumes enormous amounts of electricity, massive GPU farms, astronomical energy bills, huge carbon footprints, and every new generation requires exponentially more resources for smaller and smaller improvements. That's the definition of diminishing returns. The scary part, the industry may have confused bigger models with better intelligence, but those are not the same thing. Here's the real issue nobody talks about enough. Current AI models struggle badly with genuine novelty. Why? Because they are fundamentally approximation machines. They learn patterns from training data, which means they perform best when the answer already exists somewhere in the data they consumed. But when faced with a truly unfamiliar situation, things start breaking fast. The AI does not actually reason through the problem the way humans do. It guesses. Sometimes those guesses sound convincing, but they can also be spectacularly wrong. Confronting today's LLMs with a genuinely new problem is like watching a toddler taking a calculus exam. Sure, the toddler might randomly scribble something that looks mathematical, but there's no deep understanding underneath it. And it becomes dangerous when precision matters, because approximation works great for autocomplete, but not for reality. In high-stakes environment like medicine, science, and engineering or autonomous system, close enough can become catastrophic. That's the hidden limitation of the Embiggening. Scaling creates systems that imitate understanding, but imitation is not the same as intelligence, and eventually brute force stops being enough. There's a famous concept in AI called the bitter lesson, created by Richard Sutton, and the lesson is brutal. Methods that scale with computation usually beat human design tricks in the long run. That idea shaped modern AI. But somewhere along the way, industry became dangerously one-sided, because truly adaptive intelligence needs two things: search and approximation. And right now we have massively overinvested in only one of them. Approximation is what modern neural networks do. They learn patterns from gigantic datasets and map inputs to outputs by essentially predicting the most likely answer. That's why AI models are amazing at things like images, language, speech, and video generation. They thrive in messy, noisy, and high-dimensional environments. But here's the catch. Approximation is fundamentally probabilistic, meaning it can sound correct without actually being correct. And that makes a huge problem with precision matters. Now compare that to search. Search is an opposite philosophy. Instead of guessing, it systematically constructs solution through logic and reasoning. Think of algorithms like A-star pathfinding or symbolic reasoning system. Search excels at planning, logic, verification, and step-by-step correction. Unlike approximation, search can produce answers that are actually verifiable. The downside, it's computationally expensive and traditionally painfully sequential, which made it unpopular in the age of massive parallel computing. And here's the crazy part. The dominance of neural networks may have happened partly because of hardware accidents. Modern AI runs on GPUs, but GPUs were never designed for intelligence. They were originally built for video games, rendering graphics, physics simulation, massively parallel workloads, and neural networks fit perfectly into that hardware ecosystem. Meanwhile, search-based systems which rely more on sequential logical steps got left behind. Not because they were useless, but because modern hardware forward approximation. In other words, the direction of AI may have been shaped less by intelligence itself and more by the gaming industry. Traditional AI researchers have been obsessed with something called Occam's razor. The idea is simple. The best explanation is usually the simplest one. In AI terms, this becomes a philosophy of compression. Smaller rules, cleaner models, shorter programs. Researchers basically believed intelligence meant finding the most elegant shortcut possible. But now another idea is starting to challenge that entire philosophy, and it's called Bennett's razor. Here's the difference. Occam's razors ask what is the simplest solution, but Bennett's razor asks something much stranger. What is the least restrictive solution? This approach is known as W-maxing. Instead of building systems with rigid rules and tightly constrained behavior, W-maxing tries to keep systems as flexible, adaptable as possible. In other words, don't over-specify intelligence. Leave room for adaptation, because overly rigid system may perform well in familiar situation, but completely collapse when the world changes. And here's where things get crazy. Researchers tested this idea on binary arithmetic tasks. When they prioritized weakness and adaptability over pure simplicity, the system showed between 100 110% to 500% better generalization. That's massive, especially in AI where generalization is one of the hardest problems to solve. Why does this matter? Because true intelligence is not just about solving one task perfectly. It's about adapting to entirely new situations. And adaptability requires flexibility, not rigidity. What's fascinating is that biology already works this way. Your brain does not micromanage every tiny action. Biological systems distribute control across multiple layers. Lower layer systems handle local decision. Higher level systems guide broader goals. This creates what researchers call polycomputational architectures. Basically, highly adaptable system built from many interacting components. Nature optimized for flexibility, not perfect control. And that may be the biggest lesson AI still has not fully learned. For years, the AI industry searched for a single perfect architecture. One system, one approach, one path to intelligence. But reality is turning out to be messier and smarter. The future of AGI is increasingly looking like a fusion of two worlds: approximation and search, prediction and reasoning, instinct and deliberation. And the most powerful AI systems today are already evolving into hybrids. A perfect example is AlphaGo. People often think AlphaGo won because of neural networks alone, but that's not true. AlphaGo combined two fundamentally different systems, search and approximation. The neural network estimated which moves looks promising, then search algorithm explored those possibilities with precision. One system handled intuition, the other handled logic. And together they defeated one of the humanity's greatest Go players. That moment quietly changed the future of AI forever. Even modern reasoning models are moving in that direction. Systems like OpenAI O3 use chain of thought reasoning to simulate deeper problem solving. It's basically blending fast intuition, what psychologists call system 1 thinking, with slower structured reasoning, system 2. And then there are experimental cognitive architectures like Mars and Hyperion. These systems are designed around a brutal reality. Real intelligence operates with incomplete information and limited resources, not perfect knowledge, not infinite compute, just constant adaptation under uncertainty. This is why the future may move beyond frozen AI models entirely. Instead of giant static systems trained once and deployed forever, researchers are exploring seed-programmed architecture, systems that can grow, rewrite themselves, learn continuously, and evolve over time, almost like digital organisms. Projects like Era and Hyperon are pushing towards AI systems that behave less like databases and more like active scientists exploring reality. That's massive shift because intelligence may not be a finished product. It may be an ongoing process. And this leads to one final terrifying question. For centuries, humans treated the mind like software. Separate the body. In AI, we inherited the same assumption. We believe intelligence can exist purely as code running on machine, but biology does not work that way. In living system, mind and body are deeply connected. Adaptation happens through interaction with the environment itself. So here's the real question. Can a purely software-based AGI ever truly match biological intelligence? Or will the future of intelligence require something more integrated, more embodied, more inactive? Because the answer to that question may determine the future of AGI itself. The next leap in AI won't come from building models that are merely bigger. It will come from building systems that are more adaptive, more efficient, more hybrid, and more connected to reality itself. The era of pure scaling is ending. The era of fusion intelligence is just beginning.